Okay, so it's time to start with the second day of BTR in the Eastern Track. Welcome everybody. My name is Carlos Paradi from the University of Tokyo, and I would like to introduce our second headline speaker, Professor Tan from the Harvard Institute of Technology. I'm going to briefly read your introduction. So you received your PhD in transportation, and you're currently a full professor in the School of Transportation Science and Engineering at Harvard Institute of Technology, and also executive deputy director at the Key Laboratory of Transportation Industry. So you're long engaged in research in basic theory and applied technology for pavement structures and materials, and have published more than 200 academic articles. So we are glad to have you here, and you can start your presentation whenever you're ready.
Okay.
All right, I'm gonna stop sharing my screen and it's all yours.
I will share the video by myself.
Okay, go ahead, please.
Okay. Thank you, dear Carlos, and thank you all here for the attended the conference for this section. I will be sharing my video first because of the network maybe not is stable. So we're first to prepare the video here. Okay, now I show it. Okay. Good morning, colleagues and friends. Thanks very much to the BTR committee and Professor Jinping for the kind invitation to this conference. Yiqiu Tan from Harbin Institute of Technology. It's my honor to have the opportunity to share our team's research. Over the years, our research has been patient safety and the infrastructure durability. Today, my topic is technologies for proactive prevention and management of the ice disaster on pavement. This presentation comprises 3 sections. First is introduction of the research. As we all know, snowfall is a national phenomenon. It significantly impacts global transportation systems. China has the world's 3rd largest territory, and 83% of the pavements are located in the ice regions. Statistics with the ice and the snow caused by the winter storms, like ice and freezing rain, seriously affect traffic safety, operational efficiency, road capacity, and public livelihood. According to the winter accident statistics from 2020 to 2024, showed in this pie chart, ice-related accidents accounted for 58% of incidents, ranked as the leader cause of the winter traffic disruption. Furthermore, annual losses exceed 300 billion China yuan, including infrastructure damage, emergency response costs, and productivity declines. For example, in 2008 China, ice and snow disaster lasted 33 days, covered 96 of the highway and the urban roads across 20 provinces, was disrupting travel for over 100 million citizens. Therefore, improving prevention and mitigation capability for ice disaster is imperative. However, there is two major challenges exist in the snow disaster prevention and mitigation ability. The first challenge is the lack of the management and the control in the ice affect traffic operation process. The reason why it's difficult to assess the state of the ice and the snow on road surface, especially for black ice and the freezing rain. Second is the complexity of the ice, tire, and the pavement system, causing the not clear friction behavior between the tire and the icy pavement. The third is difficult proceed of the ice and snow conditions on the surface of the pavement, lack of the early warning methods for traffic operation. Therefore, the snowfall always result in the road networks closure. So how to develop scientific evaluation and the early warning technologies for the operational safety of icy and snowy pavement is one of the major challenges. The second challenge is the weakness of the pavement anti-icing and anti-skating capability. The conventional solution, snow and ice removal, are passive operations, like the snow melting agent, mechanical de-icing technology, manual snow removal method. These approaches present compounded setbacks, include the environment pollution, lower efficiency, and higher investment. Moreover, these methods normally cannot remove the snow and the ice very clear because of the tight bond at the interface between the ice and the pavement. So there are methods to enable to the pavement surface itself to possess anti-icing and de-icing capability. It would be the best way to solve this major challenge. For solving these challenges, we can get some research objectives need to be done as below. The first, establish the skate behavior theory of the tire ice pavement interface system. It is fundamental interfacial mechanics. Second, is proposed methods for operational safety assessment and early warning on icy pavement according to the safety potential field theory. The third one is developing active icing and skate resisting pavement, including the new materials developed and energy conversion system in pavement. The last is create a technological framework for proactive ice snow disaster prevention, providing solution to overcome disaster mitigating challenges. To achieve these objectives, our team have conducted extensive research and achieved some innovation results. First is theory of the anti-skate behavior in the tire ice pavement interface system. First, we developed the ice sensor on the surface of a pavement. The working principle of the sensor is based on that. The frequency of the piezoelectric film is sensitive to the state of the water. When the film is dry, it has a frequency. When the drop of the water on it, it has a frequency. When the drop is freezing, it has a frequency. So that they can get the different frequency with the different state of the water. From this figure, we can find the accuracy of the predicted ice thickness on the pavement is up to the 98% comparing with the real ice thickness. And also developed the system, include the ice monitoring sensor, snow thickness laser sensor, and the weather sensor, data collection unit, data analysis collector, and so on. This system would identify the ice and the snow conditions for the dry pavement, office slash, snow, and ice. So this system can instant real-time and accurate perception of the ice condition on pavement. Second part is anti-scale behavior on the tire, ice, and pavement. Because of the current evaluation methods for the icy pavement skate resistance faced critical limitations. We built the multi-scale test platform, including the micro-scale road surface ice simulator and the medium-scale road surface ice and snow simulation system, ice and snow road safety verification platform, and the full-scale ice and snow road test facility in Heihe, Heilongjiang Province. This platform can support the simulation of the ice and snow carriage and the research of the anti-slip theory for ice pavement. Following is the findings of the research. First, we found the formation growth process of the ice on the pavement and the functional decay of pavement texture. From the picture on below, we can find the degradation pattern of the road surface texture with the ice growth. And we established the approach to evaluate the ice pavement morphology. We found the evolution of the dynamic friction coefficient and the cycling loading. You can see this figure. We find the non-equilibrium evolution of the tire hysteresis and adhesion friction in the deformation recovery process. Friction performance of the road and the thermal hydromechanical multi-physics coupling. Here you can see there is a three-stage contact state of the tire, ice, pavement, and friction. You can see this figure. The zoom red in the bottom is a poor tire and ice interface and dominated by the boundary lubrication. And in the middle is a zoom pink. This part is tire, ice, and pavement composite contact. And in the blue one, top of the part is direct the tire and the rubber fraction. Now we talk about the anti-skate performance assessment model for icy pavement. Classic rubber friction fundamental field to characterize ice pavement. We established a skate resistance prediction model incorporating ice-water phase transition energy stick. This part is stand for the ice-water phase change. This model for ice pavement, considering the phase change, is increasing the accuracy up to the 34%. Furthermore, we find the key to skate resistance on the ice pavement surface is the adhesion at the ice pavement interface. We use the machine learning method to predict the friction coefficient, establish the hybrid data physics-driven friction forecasting framework. Data physical hybrid-driven model achieved high prediction accuracy, and fast response. Next is the vehicle driving dynamic stability on the icy pavement. We did the driven safety stability simulation test on the ice pavement with different types, including the straight, curves, uphill, and special kinds section. After that, we jointly established the vehicle dynamic simulation model, used the car sim and truck sim, and the winter road-driven stability was tested by the film test road. Based on the measured data, we corrected simulation value and recommended the safety speed at a different condition. At last, the approach to operate the dynamic early warning of ice pavement was set up. Based on safety potential field theory of the road driving, learning from electric field motion, we create safety assessment methodology and the safety evaluation model. A safety assessment model was developed by a comprehensive, considering multiple risk sources such as road condition, environment, vehicle, human, and management factor were taken into account. After that, the integrated safety management and forewarning framework was developed. We can see this chart. It is the classification standard for the ice and snow road operational risk warning level. Different level has different speed and the safety distance, which can break through the limit of traffic management in the ice condition, achieved a proactive disaster prevention. According to these technologies above, we developed a network-level digital warning and management platform for ice and snow operation safety. Practice showed that the traffic open rate and the ice condition improved 63%, and the traffic accident rate decreased 30%, ensuring safe operation of the traffic arteries during winter. Now, I share another technology, the active anti-icing and skate-resistant technology, include materials, system, and equipment that offer a smarter, more effective solution. First, we have developed the slow-release de-icing materials, which is a low freezing point filler. These materials adopt a dual mechanism for freezing point control. It both lowers the solid-liquid phase transition temperature and reduces sensitivity to temperature changes. Moreover, the low freezing point filler uses the core shell structure, where low freezing point components are hydrophobic shell. This design enables control release the de-icing agent, while also enhance the water repellent and also enhancing the water repellent of the pavement, effectively lowering the freezing point and prevent the breathing. This slide presents the effect of the filler in the snow removal and anti-icing. On the left, we show the test adhesion performance between the ice and the mixture. You can see the anti-icing mixture have no any bond between the ice and the mixture, but for the common mixtures, the broken in the ice layer. On the right, you can see how the additive reduce the bonding stress between the ice and the pavement surface with the different temperature. As shown by the result, both functions of the materials are proven to be effective and reliable. These materials demonstrate several technical advantages, one of which is active snow melting, that is, self-melting and light snow condition, no stick and heavy snow condition. Self-melting and light snow means it needn't any manual and mechanical methods. The pavement no any ice. No stick and heavy snow means it allows for fast and easy snow removing. Use mechanical methods. The effect is a clear showing in this picture. This pavement is built in the Beijing Daxing International Airport Expressway. In this picture, you can find in the left part is anti-icing pavement, and in the right is a standard pavement. You can see this the anti-icing pavement. There is no any ice on the pavement, and for common pavement, there is covered by the ice, so the color is visible. You can see it's black and the white. The second advantage is anti-icing and escape resistance. The application on the China-Russian Heihe Bridge deck. From this picture, you can find there is two paths. For the Russian path, these are covered by the ice, and in China path, they use the de-icing pavement. You can find is there is no any ice, and the skate resistance increase by nearly 3 times. Also, the traffic accident rate on the same road section decreased by the 38%, and the traffic fatality rate dropped by the 25. The third advantage is environmental friendliness. This is demonstrated by the application on the south to north water diversion in Henan province. First, it serves as a key east-west traffic artery requiring high traffic capacity. Second, since it crosses the south to the north water diversion project, it demonstrates to eco-friendly standard. After using materials, the pavement skate resistance improved by the 2.8 times, and the water quality and the bridge reached the Class 2 standards. This shows that our materials successfully meet the both critical requirements in the region. The fourth advantage is improve the traffic capacity. After applying the icing pavement in the Changchun, northeast of China, it significantly reduced the risk of the road icing, effectively enhancing traffic flow and driving more safety during the extremely winter weather, enhancing traffic flow and driving safety during extremely winter weather. From this picture, you can find in the left is our de-icing pavement. So the car and the truck is driving is very fast. The second materials are developed, which is self-melting and self-healing, ultra-thin, very coarse, using graphene microcapsules. Overall, this technology reduced the occurrence of the pothole and the delamination at the microscopic scale, while slowly down micro-cracking formation and development at the mesoscopic scale. This slide shows the core of the UTWC technology, graphene microcapsules. This technology addresses two key challenges for asphalt pavement in the ice and snow conditions: gate resistance and damage control. With graphene microcapsule, the picture can self-melt to remove ice and snow efficiently. It can also self-heal. It can also self-heal to prepare damage caused by the cracking and wear. This ensures safer and more durable road during winter time. We use a resin and the graphene as a multi-layer capsule wall and packed the asphalt rejuvenator inside. A two-step self-sampling process from the graphene microcapsule. This slide shows that the result of the graphene microcapsules. On the left, it shows the effect of the temperature increase and the snow melting, while on the right, it shows the material's self-healing performance. The result reveals that the strength of ice and pavement interfacial is reduced by 59%, which enables efficient de-icing and promotes micro-cracking self-healing. The healing rate, together with the temperature increase, is up to the 81%. This technology has been successfully used in the flight zone of the Xinzheng International Airport in Henan, which is the largest airport in the central China with a heavy traffic. It experiences influent by the very heavy snowfalls, along with 56 freezing thaw cycles per year. After applying these materials, the road surface temperature increased by the 10 to 12 degrees within 2 hours, and that means a significant heating effect. Above technology we talk is focused on the new built pavement, but how to enhance anti-icing and escape resistance function for the existing pavement. So we developed a photothermal superhydrophobic coating for existing pavements. This material is based on the mesostructure design and the surface modification. It includes both a photothermal superhydrophobic filler and a photothermal superhydrophobic coating, working together enhance anti-icing and skid-resistant performance. This slide shows application performance of the photothermal superhydrophobic coating. On the left, the de-icing effect is presented. At -5 degrees, the coating reduces the ice and pavement adhesion strength by over 70%, increase the surface temperature by 8 degrees, and shortens the freezing time by the 2/3. On the right, the anti-icing performance is shown. At -5 degrees, coating exists the time for the ice formed on the cold surface by more than 4 times. Therefore, compared to the conventional pavement, a photothermal hydrophobic coating demonstrates remarkable anti-icing and de-icing performance. Besides of the materials above mentioned, we still developed an energy conversion pavement snow melting system for the extremely conditions. This system can be powered by the soil and the waste energy sources, make it highly adaptable and sustainable. It is designed to meet the urgent, where reliable traffic options is critical. For example, de-icing on the aircraft takeoff and landing platform. So this system can utilize diverse energy sources, including solar energy and geothermal heating, industry waste heat, and residual heat from building heating system. It remains effective even under extremely cold conditions, with a working temperature down to minus 30 degrees. To develop this snow melting system, we built a temperature moisture coupled snow melting model. The main challenge was to improve accuracy of the temperature prediction within the model by integrating modeling methods shown on the left with a coupled temperature moisture calculation equation. We successfully increased the surface temperature predict accuracy by 42%, reached the expected performance level. At the same time, to balance the efficiency and operational performance, our team developed a multi-objective optimization strategy model. Using a genetic algorithm, we solved the model and generated the anomogram to guide the snow melting system operation. Based on this, we finally successful to propose an intelligent operation strategy for the snow melting system. We enhanced the region adaptability of the system. Our team developed a unit air heat load based design approach for the snow melting system. Based on the data shown in the table, we established the design standard for the energy conversion pavement snow melting system, matched to different regions across China. And we built the China first energy conversion snow melting pavement in 2008. As shown on the right, the system reached the expected performance within 4 and 6 hours. Demonstration is practice effective. The system is applied to the working zone of the Beijing Capital International Airport in 2015. The test result is well. In 2017, the systems applied at the Beijing Daxing Airport contribute to this major national infrastructure project. Practice have shown that all weather round free of snow and ice, ensuring operational safety without manual and the mechanical cost, saving significant labor and resources. In developing equipment, they created an intelligent laser target de-icing system. This technology used the laser point irradiation to promote the ice helmet interface separation, while laser line scanning generator breaking along the skin path by rapidly applying thermal melting. Compared to traditional de-icing methods, laser-based automatic de-icing causes less pigment damage and more environmental friendly. Beyond de-icing technology, we address the gap in anti-icing and skate resistance performance evaluation by inventing an ice and snow pigment fraction test device. We also developed a multi-angle shear stress tester. Together, this innovation formed a comprehensive active anti-icing and skate resistance technology for the construction and maintenance scene, and overcome to a challenge to the road anti-icing and skin resistance capability, achieving proactive disaster reduction. Overall, our achievements in the active anti-icing and skate resistant technology for the pigment can be summarized in 4 areas: series of anti-icing additives, anti-icing pigment coatings, friction performance evaluate methods, and technique. Based on these innovation results, we can get some concretes. First, we get concrete the theories of anti-skate behavior in a tire ice pigment system. Secondly, we developed the active anti-icing and skate resistant technologies for the pigment. And finally, we made anti-freezing design methods for asphalt pavement. That's all for my presentation. Thank you for your listening.
Thank you very much for that very enlightening presentation. I am not very familiar with pavement literature, so it was very educational. So there are a couple of questions on the chat. I guess if Kara's still here, maybe you can unmute yourself and speak directly. But if not possible, then I just go to proceed to read the questions here. So can you see the questions in the chat box? Professor Tan, can you see the questions in the chat, or should I read them?
At the moment, At the moment, there is some, sorry, can you hear me?
Yes, I can hear you.
Okay, okay. Okay, I will check. There is some the questions.
Yeah, so the first one from Dr. Koppelman is at 11:11. So how long is ice or snow covers our roadways in Beijing on average each year?
Okay, I will be, there are different, because China is a very growth and the different parts, there are different times. For the Beijing, maybe from in the November to the next March or the April, just like this. And each year there will be about the 5 or 7 times per year. And for China, for Heilongjiang province, will be from the October to next, maybe for the April or May. These times will be have the snowfall, and each year we will be have about the average about the 10 times. And each time, for example, in Harbin, for example, there is a snowfall will be the all day will be close the highway, there is will be have the fee will be lost above the 3,000 no sorry 3000万3000万是多少 billion？ 3 billion 30 billion US 30 billion 人民币元 per day. About when the snowfall will be downward about the 3 days. So each snowfall will be there is a loss about the 100 billion 人民币元. So per years, about the times, about the 10 times of the snowfall will be about 1 billion 人民币元 lost. So it will be very serious. So this is the first questions. Yeah.
Okay. And then the second question is also from Kara. She was asking whether electronic stability control, ESC, has been required on new passenger vehicles or heavy trucks in China for several years now.
It is for I'm not sure this PAX vehicle, what's the meaning?
Passenger vehicles. PAX is an abbreviation of passengers, so just like a normal, a regular.
Passenger. Okay. Yeah. Okay. You means our I'm not sure is electronic stability control is used for the monitoring of the snow or ice the system, or used for just for the traffic. If for our to monitoring of the snow, the situation or conditions, it will be longer because we are already used about the 6 years or more. But for only for the traffic, there is the visual and the others. There is a depends. For example, in the very cold region, it will be shorter times, but in the other times will be longer. So 8 hours about it's takes about already used about about 6 or more 10 years already to be used now. Yeah. So I'm not sure this is for electronic stability used for what area. Yeah.
Okay. And then the next question is also from Kara. She was talking about how much more costly are paving materials in China for these icy, snowy regions. So maybe compared to a regular area where it doesn't snow that much, how much more expensive would that be?
Okay. There is a very good questions because it's a different area. There is a different the failures of the pavement. For example, in the Heilongjiang province, it belongs to a very cold region, and this area, the failures will be serious more than the other place because it's the works the situation is more serious. For example, the asphalt pavement, the works area will be the uptime, temperature is up to the 10 degree for weather, and for temperature in the temperature in the pavement, in the asphalt pavement, is up to the nearly to the 70 degree centigrade. And for the lower temperature of the pavement in this area is up to the minus 40 degree is nearly. So I think it's asphalt the pavement is a work area of the temperature. There is a temperature lapse. There is a gap about is 120 degree nearly. So it's difficult to balance the cracking and the rotting, this kind of the fillers. So for example, in Heilongjiang or in Tibet or Xinjiang, this area also have the same times because there is a big the time lapse. So we need before we need to focus on the cracking, but because used materials will be softer than the other area, so easily in the summer times it will be have the more deformation. So there is more rotting than the other area, for example, in the Guangzhou and Shanghai and other places. So in the cold region, we need to think about it of the rotting. But if you are to meet the rotting, there will be have some cracking more. So it's difficult to deal with. So now we are ready to make the new design for materials and the structures of the pavement to united designs. So this, for example, for the up layer in the top layer of the asphalt, we use to a little soft materials, for example, the viscoelastic materials to deal with the cracking. But in the middle or the part of the bottom layer, this part where to think is about to deal with the rotting, so to meet the deformation, and for the bottom layer, we use to think it's about the reflection, the cracking for fatigue, for the other bundle of the between the layer and the bottom of the or the top of the base. So these structures to meet above the big temperature lab area, so to meet the good performance. And for the icy and snow region, also we are use this kind of structure and materials. But there's a difference is for the top of the layer, we used some, for example, we developed some new materials, especially for the icing fillers or the other materials when we designed the materials for this pavement. So to there will be have some more functional pavement, and another one for the high performance the pavement. So deal with this kind of temperature or the serious the climate is not too suitable for asphalt pavement. Yes, for this is my answer.
So what would that be like in general? Like we're talking about 50%, 100% more expensive, considering all those differences in material.
For the cost, yeah.
Yeah.
Yeah, if your thinking about the cost of just for the structures of the asphalt pavement, only for the pavement, it will be the cost is the same as the common. There is no more to increase for
Okay.
the cost. But if we want to have some some functions, for example, the icing, they will be have the increase some the cost about about 8% for the payment this layer. Yes, 80%.
Okay,
Yes.
80%. Thank you.
8%. Yes, it's not more, not very far more. Yes,
Okay, okay, it's 8%. Okay.
8%. Yes.
Okay.
Yeah.
Okay, so the other question is from myself. On slide 25, you mentioned eco-friendly pavement. So I was wondering what you meant by eco-friendly.
Oh, eco-friendly is comparing with the other some deal with the ice some the method for example the snow the agent 溶血剂怎么 melting agent
Okay,
melting
okay.
agent yes melting agents is each snowfall will be used it and will be more more to have damage to the structures of the infrastructure materials and for the soil and the other and for our de-icing materials there is no any the environment effect so where is core is friendly yes.
Okay, okay. Okay, so
Yes.
I thought you were talking about the pavement itself, but it's
Yes.
the
And
icing agent.
yes. And
Okay.
we are also tested by, for example, the soil. Yeah, there is some the plant, some the plant put in our materials. There is some the water and to water some the plants. There is no any effect. But if we use the melting agent, there will be have a very effect on the plants. So it's also is for the environment the effect. Yeah.
Okay, thank you. And then there are two more questions. The other one is also from me. So you mentioned self-healing properties of pavement.
Yeah.
So that was in slide 28, but I was curious about how does that work?
Yes. For the self-healing, because especially for in a cold region in China, where also have the freezing, so this cycling each year will be have more than 100 or some in the middle area, maybe more than 200 cycling times. So it's easily to make the materials have the damage, the damage. There is a micro, the cracking this way. So this cracking for the asphalt, if there is no any treatment, they will be have a little healing because asphalt there is viscoelastic properties. But we developed new materials where to develop these materials is the capsules. Inside, we use some repaired materials of the asphalt, and the surrounding by the graphene, this kind of materials because it will be conduct. Yeah. So when there the materials, there is the pavement. If there is a damage by the freezing and thaw, they will be have a little cracking, and this capsule will be cracked, and the inside of the repair materials will be flow into the cracks, and this one will be healing. There are little healing. This healing rate about the 60% compared with the beginning of the damage. Yes, and if we can use some a little the heating the heat. For example, we use some the electric and make the materials with a little temperature increasing. We are mentioned above the 10 or 12 degree, just like this. They will be heating more above the 81% healing. So this is our developed the new materials now already used in some airport, especially for the runway. Is to repair some damage. Yes.
Okay, and then there's a final question, which I'm not sure if I'm getting it right, but Sakdirat asked about, will the whole life cycle perspective be considered instead of construction maintenance perspective?
Yes, because these materials we are developed, there is different materials use different the part of the around life 叫什么全寿命周期啊？ lifetime, yes. So, for example, where new build is a construction for the built the new pavement, we use some de-icing materials and the other some, for example, the micro capsules, this kind of materials to use this one. But if there is a existing pavement for already used this pavement, not easily to repair the new layer to meet the de-icing the performance. So we just to develop the coating. This coating, if there is a light or for the solar, this kind of the energy, it will be heating and will be have the de-icing the performance. So this just used for maintenance this area. Yes, yeah.
Okay. Thank you very much. I don't see any other questions on the chat, but if there are no more questions, I would like to take the opportunity to give you some. Well, first of all, thank you again for joining this session, and I hope you learned a lot. I sure did. And so just a little bit of information about the next session. So we have two sessions, parallel sessions now. The first one is on this room about sustainable transportation systems. And the second one will be a different Zoom room about freight and logistic optimization. So please, the link for the other Zoom room is also on the chat. So feel free to choose the session of your preference. And again, Professor Tam, thank you very much for joining us, and we hope to see you again at some next BTR.
Okay, thanks, dear Carlos, and all the audience here. And I hope we can keep touch. And if there have the chance, we can do cooperations on this area. So I would like to meet the next times. And welcome to Harbin and to Harbin Institute of Technology to our cooperations and to our communication. Thank you very much.
Thank
Yes.
you very much.
Okay, thank you.